Okay, we're back, hopefully. So, picking up, this is the makeup lecture for the day that we missed. And in the previous video, we just figured out the nominal stated rate. Let me go back and give you the problem again, in case you're just starting with this video. We wanted to find the nominal effective rate of interest that would give us $50,000 in 10 years if we currently have $30,000, and the interest is going to be compounded monthly. And basically what we're doing here is we're looking at this as starting with the $30,000, there's going to be 120 compounding periods over those 10 years. And we want to figure out what's the interest rate over the monthly compounding period. And we did this. This is looking for I. And we ended up with I was 0.004266 per month. If you multiply that by 12, then you'll get that stated as an annual percentage rate. So it's 5.12% annual nominal interest rate. But we want to know what the effective annual rate is. So how can we figure what that means effectively? So to think about effective rate, let's go and look at over here. What we've got is 1 year goes from time 0 to time 1. And we're chopping it up into 12 pieces each month. 1/12, 2/12, 3/12, and so on. Over each of those individual months, 1/12 of a year, we increase by a factor of 1 plus I. Because I was the interest rate for each of those compounding periods. So we multiply by 1 plus I, multiply by 1 plus I, multiply by 1 plus I. At the end of 1 year, we've multiplied by 1 plus I 12 times. In other words, we multiplied by m times, because m is the number of compounding periods per year. So in general, so this is for this particular problem, in general, if we let the effective interest rate be this R EFF, so for effective, you can start off by looking at this, look at the equation, the principal amount. By definition, the effective rate is the rate, such that if you just did the principal amount under simple interest with the effective rate for 1 year, principal times 1 plus effective rate. So that's just effective rate under simple interest for a year. That's supposed to be the same as if you took the principal and then used the nominal rate, but you chopped it up into the m pieces and then compounded it m times. In other words, you get the 1 plus I to the m. So by definition, the effective rate is the rate that makes these two equal. Now, if you notice that there's nothing to do with the principal, you can cancel the principal from both sides algebraically, and what you're left with is 1 plus the effective rate is 1 plus I to the m, and you subtract 1. We get this nice little formula here that the effective rate is 1 plus I to the m minus 1. So you're taking that factor of 1 plus I, raising it to the m power. That's going to give you the factor over the entire year, but the interest rate is 1 less than that. It's not equal to that. That's going to give you the factor you multiply by, but the rate is going to be 1 less than that. So just to illustrate for this problem, let's go back up here. We had 0.004266. That means that we have 1.004266 is the 1 plus I. So that's the factor that you multiply by each month. If you raise that to the 12th power, that gives you the factor that you multiply by each year if it's compounded each month. Well, the effective rate then is going to be that minus 1, because this number is going to be a number bigger than 1, and we want to write it as 1 plus the effective rate, so we subtract 1. Instead of using this truncated number here, it's even easier algebraically if you just leave it as the 5/3 to the 1 over 1/20th. So you go back up here. 1 plus I was 5/3 to the 1 over 1/20th. If you plug that in here, you raise that to the 12th. Then 1 over 1/20th to the 12th is the 10th root, fractional exponents. You multiply the exponents, power to a power. So it's 5/3 to the 1/10th minus 1. And if you compute what that is to the nearest hundredth of a percent, it's 5.24% effective rate. Notice the effective rate is bigger than the nominal rate. That's always going to be the case when you're compounding more than once. So if you're just compounding, if m is equal to 1 over a single year, it's going to be the same. But if you're compounding it all more than once, the effective rate's always going to be bigger than the nominal rate. Okay, so let's do one more problem, because the distinction between the nominal and effective rate is can be a little bit tricky to get used to at first. So let's calculate the nominal rate of interest corresponding to an effective rate of 4.25% compounded quarterly interest. So this does not mean that the 4.25% is the nominal rate that's getting compounded. It means that this is the effective rate, and we want to say what's the nominal rate that would produce this effective rate. Okay, so we're going to go back to our formula that we went over up here that relates the effective rate and the interest rate per compounding period. That's the rate effective equals 1 plus I to the m minus 1. The effective rate is 4.25, so 0.0425 is 1 plus I to the 4th minus 1. And we want to solve this for I. So we're going to add 1, gives us 1.0425, 1 plus I to the 4th. And then take the 4th root. So again, to get rid of the exponent, you're taking a root, which means you're raising it to a fractional power. 1 plus I is 1.0425 to the 1/4, and subtract 1 gives us this. So it's the 4th root of 1.0425, and then subtract 1. And that turns out to be roughly 1.046%, or 0.01046. Now, again, this is I. So this is per compounding period, which for us is quarters. If you want the nominal rate, you have to multiply by m. So you have to multiply by 4, and that'll give you the 4.18% nominal rate. Notice again, the nominal rate, 4.18%, is less than the effective rate, 4.25%. We've just gone in the other direction here. I gave you the effective and asked for the nominal. The previous problem, we figured out the nominal rate first, and then figured the effective. But you should be able to do one from the other, both directions. Again, notice the effective rate's always bigger than the nominal rate r, unless m is equal to 1. They're going to be the same in that case. Okay. Last page. We're 3 pages out of 4. So the last page. In this problem, I'm going to show you how to find the time period. So how long does it take to get something? This is a problem that there's homework problems in the book, and I wanted to ask them in the online homework, but the book does not assume that you know anything about exponential or logarithmic functions. They go through a very cumbersome process of wanting you to graph the things on a graphing calculator and compare the graphs and see where they intersect. It's a really bad way of doing it because it's such a simple buttons that you press. There's really only a couple buttons that you press. It's a very short computation. It's really a roundabout way to go about graphing and comparing the graphs and seeing where they meet and that kind of stuff. So I'm just going to go ahead and show you. It involves logarithms, which is not a prerequisite for the class, so that's the drawback. So what I'm going to do is I'm just going to tell you the buttons you press on the calculator when you get to a certain point in the problem, and just, you don't have to know anything about logarithms. Just understand that once you get to that point, this is what you're going to press on the calculator that'll tell you how to solve for the variable. So the problem here, do you want to become a millionaire? Okay, so somebody wants to become a millionaire. David invests $300,000 at 2.1% annual interest rate compounded annually. So we're not compounding monthly or daily or anything like that. The compounding period is the same as the interest rate period. How long until David is a millionaire? So we want the future value to be $1 million. Present value is 300,000, and interest rate is 0.021. So again, we have 3 of the variables. We want to find the 4th. Go back to our, this formula should be emblazoned in your brain by now. F equals 1 plus I to the n times p. 1 million is 1.021 to the n times 300,000. Divide by 300,000, and we get 10/3 is 1.021 raised to the n. This is a different equation than we've had so far. It's even different than when we were solving for the interest rate, where we used fractional exponents. The only way that you can solve an equation like this is to use something called logarithms, which is a special kind of function that you normally study in college algebra or sometimes intermediate algebra. I can't assume that you know this, but I'm going to show you how to solve this for n. Even if you don't know anything about logarithms, I'm going to show you what to put in the calculator. So any equation, not just this one, but any one where you have some number equals some number to the n, and you want to solve it for the exponent. How do you solve for the exponent? Here's what you're going to do. Look for one of 2 buttons. There's going to be one button that'll say log, another one that says ln. You can use either of them. You should get the same answer either way. It's a special property of logarithms that it doesn't matter what the base is. When you're solving one of these equations, you're going to get the same answer. So, 6 of one, half a dozen of the other. Eeny, meeny, miny, mo. Choose one of them. Okay, what you're going to enter then is, it's going to be the log of the number on the left, so the log of the number that doesn't have the exponent, and you divide that by the log of the base of the exponent. So if it's b equals a to the n, you take the log of b. So if you're doing like the TI-30XA or 83, you can do log parentheses b. If you have some other kind of calculator, you can do b and then hit the log button, and it'll tell you the value of log b. And then you divide that by log a. So the expression literally is log b divided by log a, or ln b divided by ln a. Let's use the log, so the log button. If you use that button, if you do, on this particular one, we have 10/3, so you're going to take log of 10/3. You should get, if you're using the buttons correctly, 0.52288. Then for the base of this exponential expression, 1.021, log of 1.021, you should get 0.009026. So to find the time period, to find n, you just divide one into the other. So it's this number divided by this number. And when you take that quotient, it's about 57 years and 11 months. So hopefully either David is very young or he can get a hold of more money, because that's a long time to wait to become a millionaire. So we're going to do some more problems later in the next couple of weeks, where we have to do solving these kinds of equations. It's not going to come up too much, but it will occasionally. But we've done all 4 variables. So we solved for f, solved for p, we solved for I, we solved for n. We also looked at comparing the effective and nominal interest rates. So this covers pretty much all the different kinds of problems. 90%, I would say, of section 10.1.